to not unpause my recording. When I was messing with my audio earlier, I muted my computer completely so I could not hear you. So now I think I'm good. Thanks, Aaron, for typing that in chat. And if I ever ignore you like that, Gabe, just assume that I didn't hear you and type something to me. All right, so this looks rectangular, and it is indeed rectangular. We've got some length times some width. So just call this length, this width, and the area of a cross section is length times width since it's a rectangle. The length is the easy part on this one. What's the length of every rectangle that I draw like this? 6, that's right, 6 feet. So the area is 6 times the width. And now our job, which turns out to be probably the biggest problem in this problem, or the thing that's most problematic for us, is figuring out an expression for the width in terms of where you are along the depth of that water. You know, are you down here at 0 feet at the bottom, or are you up here at 1 foot at the top, or are you somewhere in between? Notice that as you move up this trough, the width becomes wider and wider. At the bottom, the width is 0. At the very top, the width is 2. You're going from -1 to 1, and it increases steadily between those two values. So we need an expression for the width of that rectangle in terms of its depth, in terms of y. And all we know is y equals x squared. So let's add in our coordinate system. I'm going to put my y-axis right there in the middle. Here's the point 0, 0. And my points already fit there then, my -1, 1 and +1, 1. And I need an expression for width in terms of y. So that width is the distance all the way across here. Maybe I should have done that in blue again, just darker. There's my width that I'm trying to get an expression for. And I'm going to make the claim that whatever that width is, it's 2 times the x value. So take a peek at that for a minute and see if it makes sense. No matter what x value you are at, the width is twice the x value, assuming positive x values. So for example, if this is the point x, x squared, or xy, the width is twice the x value. Does that make sense? Gabe, does that make sense to you?
Yeah, I mean, well, that wasn't my question.
I know it wasn't. I'm just picking on you.
Oh.
Aaron C, is that good?
Confusing. It's still confusing.
Who said it's still confusing?
Not Gabe.
You again, Gabe. So notice though, this is the x value right here. X is just that distance from the y-axis out to the curve. This is sort of like what we did with the slicing problems with volume. That distance is an x value.
When did we do slicing with volume? When did we do that?
We did that way back in the previous chapter, or at the beginning of the chapter. Not the previous chapter. At the beginning of the chapter, after we did area, we did volume by slicing.
Oh,
you did the homework.
Wait, you know I did the homework?
I think you did the homework. Did you not do the homework yet?
Well, I'm on the water pumping one right now, so if it was before that, then I did it.
Absolutely. Yep.
Okay.
Okay, so the width is 2 times x. The reason it's 2 times x is because this is the x distance, and then this distance is also the same, right? That's another x. Theoretically, absolute value of x. But if we take the positive x value, then we should be in good shape. All right, width is 2 times x. That means area is 6 times width, 6 times, 2x. And we're still not there yet because we need to get this area written in terms of our height or our y value. So now our job is to write x in terms of y. But remember, y equals x squared. So x equals what?
Square root of y.
Square root of y, yeah. So area equals 12 square roots of y. So for any height, for example, if we're at 0, the area of a cross section is 0, and that makes sense. If we are at a y value of 1, the area of the cross section is 12 times the square root of 1, or 12 units, 12 square units. And that fits because we are 2 units wide at the top. So let me grab this guy. We are 2 units wide at the top and 6 units long. So we're 2 by 6. At various levels in between, our width goes down from 2 all the way down to 0. All right, so we've got our area function. Our volume piece then is the area times the thickness. But the thickness is just the delta y, which in the limiting sense is going to be our dy. And so this is starting to come together. What other piece do we need? Well, to get weight from volume, we multiply by weight density. So our weight piece looks like 12 root y square root of y, or delta y, times the weight density of water, and they wanted you to use 62 on this one, right? I think. Yeah, they didn't say 62.4 this time. They said 62 pounds per cubic foot. So this is our 62 pounds per cubic foot. And then the last thing we need to put this together in order to get our work, so in our work formula, it's going to be an integral, 12 root y. I actually want to do that in a little bit different order. We'll go 62 times 12 root y times dy. Y ranges from the bottom at 0 up to the top at 1, 0 to 1. And the piece that we're missing is that the distance that each piece is moved. So let's look at a few little examples to see how this works. If we're at a y value of 0, all the way down at the bottom, we have to move all the way to the top. We move 1 foot. If we're at a y value of, let's say, 1/4, how far do we have to move? Do we move a 1/4 foot? Do we move a 1/2 foot? How far to get to the top? So for example, if this is y equals 1/4, how much is left?
1/4 minus x.
Nope.
1/4 plus.
For the specific value of y equals 1/4, how far do we have to move up? And remember, we're looking at this in terms of the y value, not the x value.
Oh. Yeah, I don't know.
3/4. Thanks, Merrick.
I was gonna guess that too,
One
but
minus
that's like 5
one
times.
minus 1/4 or 3/4. 1 minus 1/4. Generally, if the y value is just whatever you pick, some specific y value, y sub k, we're going to move 1 minus that y value. So in our integral, the factor that we get here is 1 minus y. Had this trough been 3 feet deep, this factor would have been a 3 minus y. Other things would have changed as well, but this factor would have been 3 minus y because we've got to get all the way up to the 3-foot mark, and then we're subtracting the level we're at already. So it's just a distance between two y values. And to find a distance between two y values on a vertical line, you can just subtract them. And there's our setup. So we are pretty much all set. I think, Gabe, you asked if we could go through this all the way, and that's fine. So somebody out there should multiply 62 by 12 for me.
I asked if you go through the other one all the way.
We can. Will you multiply 64 by 12 for me?
$768 according to Siri.
What'd you say? 62 times 12 is what? It's got to end in 4.
124.
How much?
$744. I thought you said 64 at first.
744. Okay.
Yeah, I
Thanks,
thought you said
Caitlin.
64.
Oh, I see.
Not 62.
I see the errands, and Caitlin got that for me. Okay. So work is 744 times the integral from 0 to 1. Square root of y is y to the 1/2 times 1 minus y dy. And if you're integrating this by hand, you're going to have to multiply out. You're going to have to multiply out the y to the 1/2 times 1 minus y. So 744 times the integral y to the 1/2 minus y to the 3/2. You're adding exponents there from 0 to 1. So 744, oops, it's gonna make me, no, I'm gonna try to sneak this in over here. 744 times y to the 3/2, that's not gonna work. We're gonna erase that and go to the next page. This is the one thing I don't like about this whiteboard, is that I can't slide it up so that I can still see most of this. We'll be able to go back to it, but we're going to add a new page. So we've got 744 times y to the 3/2 divided by 3/2, or times 2/3. And then, now I can't remember. I'm going to go back to the other page. It was minus y to the 3/2. So minus y to the 5/2 divided by 5/2, or times 2/5. And then evaluate from 0 to 1. So it looks like 744 times 2/3 minus 2/5. And our units, these are work units, and we were working in pounds and feet, so foot pounds. Although you're not going to enter the foot pounds because they said leave the units out of your final answer. So is that good from there? 198.4. Thanks for doing the calculations, Aaron. That seems pretty reasonable. 10 minus 6, 4/15 times 744. Yeah. Is that one good for you, Aaron? All right. Now for the next one, for the one that Gabe asked about, I am going to, I'm going to do a new page so that we'll start fresh. And Gabe's problem, let me see if I can go back and find it in, there we go.
I have a question. Why do these
This
problems
one
take
was an
so long?
inverted cone. So we've
Why
got,
do they take so long?
what'd you say?
Why do the questions take so long?
Because they're things that you have to think about.
Okay.
Right? Now, remember, if you're doing one of these, like say on a test or something where you're timed, remember it is okay to, once you set up an integral, it is okay to use technology to calculate that integral. So I would have been okay with you calculating the integral we set up using your calculator or using Mathematica or anything. Okay? This one has a height of 6 meters. Height of 6 meters. And a base radius of 4 meters. It's 4 meters. Tank is full of water. How much work is required to pump the water over the upper edge until the height of the water remaining in the tank is 2 meters, round to the nearest integer? So we're sort of interested in this 2 meter level. And notice that all of the cross sections this time are what shape? Circles? Yeah, thanks, Aaron. Okay, so cross sections are circles, and the area of a circle is pi times radius squared. So really, if we want to try to, as we do more of these, make them work a little bit faster, the key piece is going to be to figure out that radius expression. And we need the radius in terms of y. So I'm going to put my 0 down here up to 6 meters at the top. Cross sections are circles, and I need to write radius in terms of the y value. This will be my point 0, 0. This could be my point 0, 6. This would be my point 4, 6. Notice that instituting that coordinate system on top of your cone is going to be helpful in sort of sorting things out. All right, so this is like the one we did last time. We have a height of 6 feet when the radius is 4. When the radius is some other value, we have a height of y feet. So we're going to use similar triangles like we did in class last time. And radius compared to y is always going to be equal to 4/6. So that's just going back and using some concepts from geometry that when we cut those cross sections through the center of that cone, those cross sections are triangles, and those triangles are going to be similar to each other. Remember, corresponding sides of similar triangles are proportional. So 4:6 as radius is to y. That means that the radius is 2/3 y. And from there, we can write out our area function. Area is pi times radius squared. or area equals 4 pi y squared over 9. Now let's see if we can just put this together in all of the pieces that we need. So we know we're going to have an integral. I'm going to do the limits last, so I'm going to save those for last. We need our weight density, which is 9,800. We're working in metric units this time. We need our area piece, 4 pi y squared dy. That actually gives us our volume. So here's our area, the 4 pi y squared. It's not letting me do it. The 4 pi y squared is my area piece, multiplied by dy gives me my volume, multiplied by the weight density, 9,800 newtons per cubic meter, gives me my weight. And then the only other piece I need is my distance moved, which I don't have in here yet. And I think Merrick just said in Newton they did this as 6 minus y. And that's what's here, right there. Merrick, I hope they did it as not r over 6 minus y. Is that a quotient? Because we definitely need that area piece. Oh, okay. So what they did in Newton then is they probably have their coordinate system flipped. I have 0 at the bottom. They probably put 0 at the top. My personal preference is so that the radius piece is a little simpler. It makes, if the radius piece is simpler, it means that the distance move piece is going to be a little bit more complicated. So the way that they did it, they would have had the 6 minus y in the in this expression. I'll just circle it. They would have had it in here, whereas we have it over to the right in the distance move section. When they put it over to the left, then they have just a plain y in the distance moved section. So it is truly a matter of preference in terms of how you like to draw your coordinate system. I like to try to put 0 at the bottom and make that radius simpler.
This problem is confusing. That's all I gotta say.
Okay, I think we did one like this right in class last time.
Yeah, we did, but it was confusing then too.
Okay, so we're just looking at another one. So, but take a look at this. If you set up your coordinate system and come up with an area piece in terms of y and a distance move piece in terms of y, I'm going to call it d of y for distance. And then you have your density. And then you have your little thickness piece, so your variable of integration. That's really the vertical change. That's your delta y piece. Then those are all the pieces that you need. So I think the first and the fourth are kind of free, right? The weight density is free, and the fact that we have a dy there is kind of free. So the difficult pieces are the area function and then the distance move function. You can set up your coordinate system any way you want. And math geeks don't always choose the best way to set up the coordinate system in my experience. So I'm much more fond of setting this up with 0 at the bottom and moving up. Their coordinate system has 0 at the top and moving down. We all see things differently. Now I'm almost set up, but what's missing from my setup?
The stuff at the beginning.
Yeah, the limits. All right, so what were we doing? We were
0 to 6.
not removing all the water. This thing was full of water, and we were removing it until it was to the 2 meter depth.
So wouldn't it be from 2 to 6?
So it would be from 2 to 6.
That was a good guess.
Okay, so let me just, we can evaluate this, and we should get, let's see, 9,800, I'm gonna pull all this stuff out, times 4 pi over 9, integral from 2 to 6, and then I'm gonna distribute my y, 6y squared minus y cubed dy. So somebody go ahead and evaluate that integral for me, making sure that you then multiply by 9,800 times 4 pi over 9. And remember also that your limits are 2 to 6. I don't want to spend class time grunging through that integral. I know you guys can integrate polynomial functions and then multiply by constants. So let's go ahead and calculate that. Use whatever technology you have handy. And
I got a whack answer, but it could be right.
so
But
some number of Newton meters or joules. What's your whack answer? Let's see if you guys give us one answer. Type it into the chat.
1,313,604. 0.6. But you have to round to the nearest integer, I think. So it'd be 605.
It would be 605. Okay, we will undo that for.
I mean, I think so you round it. It's 0.608, so you round it up.
Okay. Does somebody else have that same answer? I mean, I'm not surprised that that answer is so large, because if you think about it, we roughly have 1,000 here times 4 pi on the outside. So the outside factor is about 12,000, or at least on the order of 12,000. I don't know what just happened there. So, and then you're multiplying by the value of that integral, which has a cubic and a quadratic function in it. So I'm not surprised that it's a pretty large number. So looks like on the order of 1.3 million. Do we have confirmation from someone on that calculation?
Merrick got it.
Okay, Merrick got that too. Thanks, Merrick.
The actual integral, if
now,
wants to know.
So Caitlin said that they did that on hers too. Yeah, because they're gonna probably do the same thing. We're not gonna recalculate, but I'm gonna show you what this would have looked like with the other coordinate system. So I'll draw this in blue. So the other coordinate system would have gone from 0 to 6. Okay. And we had level y, level 6 minus y. And now we're going to have level y, level 6 minus y, just reversed. It's the only difference. So in our integral, we're going to still have our 9,800. But in that radius piece, you're going to have 4 pi times 6 minus y squared over 9. And then plain y for your distance. There's one other difference, and I guess maybe this is where they like this as the preference. They're going to integrate not from 2 to 6, but from 0 up at the top down to 4. So it's still a 4 units, but it's 0 to 4. So I guess that ended up being a little bit nicer because the lower limit was 0, but we can use a calculator to do that anyway. We should get the same exact result. So there's the setup with the flipped coordinate system. That one is there. That one is there. Okay, so take a deep breath, take a peek at that. And then I think we'll look at who asked. Caitlin, was that you who asked, could we look at hydrostatic force?
Yeah, that was me. This did kind of answer my question though. I was just wondering, in that one, I couldn't quite understand why they put the coordinate system, so that this helped me kind of clarify my question. But I
Okay.
can post it in the chat still if you want to, if we can go.
Yeah,
over
why
it.
don't you go ahead and post it in the chat, because those problems come after the pumping problems, and I'm guessing that other people, even if they haven't gotten there yet, might end up with a similar question anyway. And then I'm
Okay,
going to
so
go
I just
back.
posted it.
I'm going to go back to Merrick's question. He said, when we do these pumping problems, is it as if someone is pushing down onto these cones and then the water comes over the edges? I guess I'm trying to get a better pictures of what they mean by pumping. Merrick, I would look at it more like this. There's a pump. Think a submerged pump, a submergible pump, tossed in that water somewhere, and then the pump is running, and you've got a hose or some sort of piping system, and you're just pumping the water from the pump up through the hose up to the ground level or up to the top of the container. Now, the tricky thing there is that then you think, well, if my pump is submerged, all of the water is moving the total distance. And in theory, it is. But in terms of work done, remember, it's the net difference in how far it's moved. So
Wait,
if that water was at the 3 meter level and it goes up to 6, it's moved 3 meters. Even though in reality, what it did was go down to the bottom and then back up. Because that's what has to happen, right? In theory, if you've got a pump in there, in practice, the water is going from the 3 meter level down to the bottom and back up, but the net movement is just from 3 to 6. Gabe said, was the last question in kilojoules? It was in joules. Newton meters. We had everything measured in Newton meters, and a Newton meter is a joule, not a kilojoule. Oh, they wanted the answer in kilojoules? Okay, so how do you convert from joules to kilojoules? Great question. Okay, how do you convert from meters to kilometers? What does the prefix, thanks Caitlin, divide by 1,000? The prefix kilo means 1,000. A kilojoule is 1,000 joules. So if you divide that answer by 1,000, you should have your answer in joules. So 1313.605 or 1,314 if they wanted it to the nearest whole number. Thanks, Aaron C.
Wait, what was it if they wanted it to the nearest integer? What was it?
Well, I mean, look at the number again, Gabe, right? You're going to move your decimal 3 places to the left and then round to the nearest whole number. So what is it?
1314?
1314, yeah. All right.
Thanks.
I'm going to scroll back up here so I can see Caitlin's problem. Yes, Caitlin. Thank you for typing that out. The ends of a tank are shaped like inverted isosceles triangles with base 7 feet and height 2 feet. Base 7 feet and height 2 feet. What is the force on one end of the tank if it is full of water and round to the nearest integer? Okay, so let's just draw a picture of this. Inverted isosceles triangles. Okay, so there's my tank. Not drawn to scale, but that's okay. Height 2 feet and base 7 feet. So 7 feet across the top. What is the force on one end of the tank if it's full of water? So this time we're not looking at work. Oops, cancel that. We're not looking at work done. We're just looking at the force, and I don't really need that last line. We're just looking at the force of on the end of the tank, so on that triangular face. So you can kind of think about submerging a triangular piece into water, and there's some force that's pushing against the end of that tank. Now this isn't a triangular shape, but picture a fish tank. There's some force of the water on the sides of that tank. The fish tank is a little bit easier scenario because all of the sides are rectangular. But we're just looking at the force on that end piece, the piece that's the triangle. Also notice that the other piece that makes this a little bit difficult is, so if I've got a piece of paper and I want the force of the water on the piece of paper, there's less force at the top than there is at the bottom, because this part of the paper, assuming this thing is submerged in water, has way more water on top of it than this part of the paper. Does that make sense? So if I've got this, just picture a triangular plate submerged in water, in order to figure out the force on that thing, what I'm going to do is I'm going to add up the force all the way up. So another integral. I'm going to look at the force at level 0, level 1, level 2, just up to level 2 feet. Now, our force integral looks very similar to our work integral, but in the force integral, we don't need that distance moved. So what do we
Why
need?
is that? We don't, so we in the force interval, we don't need that distance moved.
We need it's not moving. I should say it that way. We need
'cause
that distance, but it's
a-
not moving because we're not lifting it up.
Okay, that makes sense.
Okay, so the picture that I really need to focus on is just this triangle. And I still didn't draw it right, but that's fine. 7 feet across, 2 feet deep. So I'm focusing on the end of this thing. And again, I can put my coordinate system anywhere I want, but I need to have some sort of expression for the width of this thing. So in other words, the force again is really just the weight of the water, right? That's sitting on top of any little bit. So I need this width expression, which I'm going to make the case that just like before, width is 2 times x. And I need my thickness, which is again a little dy. And these two pieces together give me my area. So the area piece is going to be 2x times my dy piece. And so to get that x again, I'm going to have to solve for it in terms of y. So where's my coordinate system? I really do like 0, 0 at the very bottom. So this is 0, 2. And then I'm going to claim that this is 3.5, 2. Does that make sense? We're 7 feet across at the top, so 3.5 feet wide. Now, the last problem that we had, the one with the parabola, was actually a little bit nicer than this one because they gave us the equation of the parabola. They gave us y equals x squared. So we were able to solve for x in that equation, and then we had that expression for the width. All right, so how do we get x in terms of y? Well, I have 2 points here. I have 0.00 and I have 3.52. And what's connecting them? What type of curve is that?
Linear?
It's linear. And it's not only is it linear, but it's linear and it passes through the origin. So all I really need is the slope to figure out the equation of that line. So let's see, y equals slope times x. And the slope is, let's see, we go up to and over 3.5, right? So y equals 2 over 3.5 times x. I really don't like that decimal in the denominator, so I'm going to call that 4/7 x. Multiply top and bottom by 2. And that means that x is 7/4 y. And so my area function is 2 times 7/4 y times dy. And let's just do a quick unit check. Y is measured in feet. Dy is also measured in feet. Feet times feet are feet squared, so it really makes sense as an area piece. Now, to get the force on this, we need to know how deep it is. And we also need to account for the weight density of water. So what does my integral look like? So I think they used rho times g for weight density. What'd you say?
2 to 7.
Say that again?
2 to 7.
2 to 7. Hang on, I'm not sure about my limits yet.
Oh.
Let's come back to those.
Oh, okay.
Okay? Because this thing is completely submerged, right? 2 feet is how deep it is. 7 feet is how far it is across at the top. And it's completely submerged. So my weight density is, this was all in feet, right, Caitlin?
Yes.
Yes. And did they tell us to use 62 or 62.4 this time?
62.4.
Okay, 62.4. Then we want our area piece, 7/2 y dy. So those two parts. And the way that they usually write this in formulas in calculus textbooks is this is w of y. So that's the width piece, and then the dy gives us area. And then this piece is our depth piece, or d of y. And the depth piece is, well, 0 is down at the bottom. So the depth of any spot along the way is going to be 2 minus y again. So there's a nice little hydrostatic force formula. The only thing missing are my limits. And we just have to be careful about where this thing is submerged. So I'm going to go read Caitlin's problem again. The tank is full of water. So it's not a submerged tank, but it's just like a submerged plate. And the top is really the top. So it's not like it's dunked down an extra meter or anything. So my limit should be 0 to 2 because that's how far it is under that's where the water is, all the way from the bottom to the top. So that integral should do the trick for you, Caitlin. Are you good on that once we have the setup?
Yep, that's kind of what my question was on.
Okay, and then that should pull them together. So if you have more problems to do, it should be that same piece. You're going to need that width function and the depth function. And if you have both of those, these things start to come together a little bit more quickly.
Perfect, thank you.
You're welcome. Okay, Gabe, you gave me another problem, and I'm going to contend that that problem is the same as the problem you gave me before. So let's look at the difference. Height of 12 feet and base radius of 8 feet, full of water. And we're going to pump it out until the height of the water remaining is 10 feet. So how is this problem going to compare to, let me see, there's that one, to that problem? What changed? What'd you say, Gabe?
The height and the radius.
The height and the radius changed. Yep, that's it. And
So
the fact that you're gonna pump out just until you're at 10 feet. So the difference here would be my limits would be 10 to 12. And then I would have a different ratio for my radius over Y value.
So can we run through that real quick?
I'm going to see if there are any other questions first, because this is truly identical. We're just changing numbers. So let's see if there are any other questions first. Okay, so there's a new one.
The test at all?
What'd you say? I didn't see any other questions, so we'll go ahead and draw this one out.
Okay, do you do curve tests?
Do I curve test? No. Okay, so here we go. There's our inverted cone. We've got a height of 12 feet. So we're going 0 to 12. 0 to 12. We've got a base radius of 8 feet. So we know that radius compared to Y value is 8 to 12, or radius is 2/3 Y. So literally you are correct in that the radius and height were different. However, notice that the ratio is actually the same. So the area of a cross section is still pi times radius squared. That's going to be pi times 2/3 Y squared, or 4 pi Y squared over 9. So that piece is the same as before. Our integral, 62.4 times our area piece, 4 pi Y squared over 9, times our distance moved piece, which is slightly different from before, but not much. It's 12 minus Y, because this tank was a little taller than the previous one. our dy, which gives us our thickness. And then we just need our limits. So our limits, we're only removing, oops, cancel that. We are only removing up to the 10-foot piece. So if we look at our coordinate system, we're removing the water that sits from 10 to 12. So those are our limits. And there's the setup. Thanks, Aaron C. You got 19,865, and that would be foot-pounds.
That is a multiplication sign between the 62.4 and the 4 pi y squared.
Absolutely. Absolutely. And if it wasn't there, it would still be multiplication, right?
I mean, I couldn't tell if it was a minus or plus, but I just want to make sure.
Okay.
So that is in foot-pounds.
Yep, because foot-pounds are units of work, and all of our work that we did was with units of feet, right? And
Yeah.
units of pounds per cubic foot, that's 62.4. So yes,
So do I have to divide it by 62.4, or is it already in pounds foot? It's already in pounds foot, right? Or feet pounds, I mean, sorry.
62.4 is what gives us the right units. If we didn't multiply by that, we would get the wrong answer. So you don't want to do all this work and then divide by 62.4 when you're done. This integral that we set up is the correct integral.
For foot-pounds.
And yeah, if you're not convinced, let's look.
No, I'm convinced. I was just clarifying.
Okay. But I mean, if you want to check, remember what you can do. Pounds per cubic foot times, okay, y was in feet, so that's feet squared. 12 minus y is also in feet. dy is also in feet. So just checking units. This foot and this foot squared cancels with this foot cubed. And the units that are left are foot-pounds. It's actually a really good exercise to do that, because then you'll make sure that you're not missing a dimension. For example, if you forgot the 12 minus y, your answer would have been in pounds only. And you say, oh, wait, that's not work, that's just force. I've done something incorrectly here. Okay, any others? All right, so some reminders. Wrong class. Wrong class. Here we are. Some reminders, your test number 2 is due on Sunday, and it goes through the hyperbolic functions. I actually didn't give you any extra homework problems on the exponential growth and decay or the integrals involving logarithms. We did a little practice with those, I think, in some of the problems that we came up with back in sections 2.4 and 2.5, but we'll hit enough practice on integration in chapter 3 anyway. So after the application problems dealing with pumping water and with hydrostatic force, the next problems you're going to see are going to deal with those hyperbolic functions. And so those should be, I think, pretty straightforward. Again, remember, you can use your calculator or Mathematica if you want to calculate anything for all of these application problems. That's going to change a little bit in chapter 3 because chapter 3 is about calculating integrals. So on those, I'm going to ask you to do a little bit more work in terms of evaluating integrals by hand and showing me all of your work that you're doing to get that. So other questions? If I were to make things up for us to do today, I would be moving on to chapter 3, and I don't want to do that to you because I know you have a test due, and I also know you still all have homework to do. So if you want to just go back and work on homework for the rest of our time, I am cool with that. And then you can maybe get caught up if you're a little bit behind, or move ahead if you're caught up.
Can you leave the?
Or maybe go take your test. I'm sorry, Gabe, did you say something?
Yeah, I was gonna say. Never mind.
You sure?
Well, I was just gonna say if you could leave the Zoom call open, that way we could ask each other questions if we needed to.
Absolutely, I'll do that.
Okay.
I'm probably gonna turn video off, but I'll leave the audio on, and I'm gonna run to the bathroom and take a little break. I drank too much Diet Coke this morning. So I'll just leave the Zoom open. So if anybody wants to stay here and work on homework, you can do that. And then if you run into trouble, you can ask. But be prepared to go ahead and write on the whiteboard and then and share your screen.
Okay.
Okay. I am going to stop the recording though, just because it's probably not necessary to record people's individual questions.
And will we be able to complete the homework even after midnight tonight?
You can always complete the homework after the due date. So there's no penalty on late homework as long as you get to the 100% mastery. You can still get 100% on it.
Okay,
so if you don't finish by midnight tonight, say you're on that last section or something, you can just do it tomorrow. And once you get to 100%, your grade will get replaced.
Okay, perfect. Thank you.
Now, what if we're at 99%? Do you only get 99%?
No. Actually, after the due date, you got to get to 100%. So you got to reach 100% mastery to improve after the due date. So if you're at 70 right now and you finish tomorrow, or whatever day it's due, it's not tomorrow. It would be the end of the day. It's due on today is the 23rd. I've got my dates mixed up. Yeah, if you finish tomorrow, then in order to get 100%, you have to get to 100%. Or in order to improve, you would have to get to 100%. But you can always, and you could do it tomorrow or you could do it next week or whenever. But you can improve it after the due date as long as you get to 100%.